Hi, my name is Adam Mars. I'm a senior graphics engineer in Nvidia, and today I'm going to talk about RTX Global Illumination, or Rtxgi for short. Rtxgi is a new software development kit that provides scalable, real-time solutions for global illumination using ray tracing. To get started, let's take a step back. 2 years ago, Microsoft introduced the first hardware-independent GPU ray tracing API with DirectX ray tracing. At SIGGRAPH that year, we announced the Turing GPU architecture and our RTX series of GPUs, which provide hardware acceleration for DirectX ray tracing and other APIs. This was an inflection point in real-time graphics, making it possible for new games to ship with visual effects that weren't possible before. Since then, games like Battlefield 5, Control, and many others have released with more accurate reflections, shadows, transparencies, and more, all made possible by real-time ray tracing. The constraints and possibilities of real-time rendering have shifted, and now we have the opportunity to reinvent the way we approach rendering algorithms. Global illumination is a computationally intense and visually important effect that can benefit from this shift in possibilities. Diffuse global illumination is so important that a lot of techniques have been developed over the years to simulate it. I've listed a handful of those solutions here, sorted into categories, based on how the GI problem is approached. Although there are quite a few ways to solve the GI problem, a familiar quality versus performance trade-off has limited the effectiveness of the solutions. GI solutions are typically either high quality, but prohibitively expensive to run in real time across a range of hardware, or they fit in real-time frame budgets but have fundamental limitations in how visibility is handled when lighting is sampled and stored in intermediate world, camera, or screen space data structures, causing visual artifacts. The new flexibility real-time GPU ray tracing provides enables us to change the dynamic of this long-standing trade-off. And last year at GDC, we introduced a new algorithm that does just that. In a talk titled Dynamic Diffuse Global Illumination with Ray Traced Irradiance Fields, Morgan McGuire describes an approach based on irradiance probes that uses real-time ray tracing to remove the visual artifacts caused by insufficient visibility information in an irradiance probe-based data structure. I highly recommend watching this talk, it's great. It's available for free in the GDC Vault at the link shown here. The algorithm and results presented in this talk were the beginning of the next wave of ray-traced algorithms that remove long-standing limitations. But we also want to make it easy for everyone to take advantage of these breakthroughs without having to reinvent or re-implement what is shown in talks like this one. To this end, I'm happy to announce the launch of the RTX Global Illumination SDK, a free software development kit that aims to make it easy for you to tap into the power of ray tracing for global illumination. Positioned between the DirectX ray tracing API and your application, the Rtxgi SDK provides global illumination solutions that use the flexibility of ray tracing to deliver image quality and performance not possible before. There are 3 high-level goals we've kept in mind while developing the Rtxgi SDK. First, we know every game presents unique challenges, so we're striving for the SDK to be flexible and customizable so you can tailor it to your specific needs and meet the challenges specific to your project. Next, scalability. We're including solutions that reliably scale across a variety of hardware, so you can rely on a single GI solution and avoid the complexity of multiple hardware-specific code paths. And last but not least, convenience. Implementing and optimizing the latest and greatest algorithms can be time-consuming and difficult. We're doing this so you don't have to. To meet these goals, we are releasing the Rtxgi SDK with full C++ and HLSL source code. We have created a sample application that demonstrates how to use the SDK and its features. Full C++ and HL source code is included for the sample too. The Rtxgi SDK runs on all DXR-enabled GPUs. This means Nvidia Turing, Nvidia Pascal, and other vendors who support DXR. The SDK provides scalability options for hardware ranging from the GTX 1060 6GB all the way up to the RTX 2080 Ti. And even better, the SDK is available now for free. We're providing the source code through GitHub to make revision control as convenient as possible and lower the friction when you move to future versions of the SDK. We're also using GitHub as the central location where you can report bugs, get support if you have questions, and submit pull requests if you'd like to contribute back. Head over to the Rtxgi page on developer.nvidia.com to request access to the SDK. With the first release of the SDK, we're providing our implementation of the Dynamic Diffuse Global Illumination Algorithm, or DDGI for short, that I mentioned earlier. To refresh your memory, the DDGI algorithm is based on irradiance probes. Irradiance probes have been around since 1998 and are supported by most game engines today. In a nutshell, you fill the 3D world with small probes that measure and store diffuse GI. Until now, the lighting stored in these probes has typically been pre-computed offline and then sampled at runtime. In the best case, the quality is excellent, but probes leak light and shadow when sampled away from the probe centers due to a lack of visibility information. This problem is well known and has been talked about for years. If the lighting changes radically near a probe because of a wall, light can bleed inside of a room from the outside sun. If the probe lands inside of a wall, then all it sees is darkness, and shadow can bleed everywhere. This often leads to artists manually moving probes to some good location and manually placing blocker geometry to separate inside and outside. That's a big workflow cost, and it doesn't solve the GI problem if you want dynamic lighting with moving characters. A character might be covering a probe no matter where you place the probe. DDGI solves the leaking and dynamic lighting problems with ray tracing. Here's the basic flow of the DDGI algorithm. At scene authoring time, artists place volumes that contain DDGI probes in the 3D world. Then at runtime, rays are traced and shaded from active probes in relevant volumes. The results from the ray trace are then blended into the probes, storing irradiance and the distance to the geometry. Finally, diffuse GI is rendered in screen space using the ray traced probes. The distance stored in the probes is used to determine visibility and eliminate the light and shadow leaking problem. Note that during the ray trace and shade step, existing probe data can be used during shading to create infinite bounce indirect lighting. The middle two steps are the critical new tasks being performed at runtime, compared to traditional irradiance probe algorithms. Importantly, these two steps are very scalable, since they are both independent of screen resolution and frame rate. Another way to say this is that the total number of rays traced is tied to the number of active probes, and each individual probe can be ray traced and updated at arbitrary frequencies. This flexibility creates a lot of optimization opportunities and the ability to adjust workloads for a wide range of hardware. To summarize, the DDGI algorithm brings several benefits to bear, including infinite bounce indirect lighting that works regardless of the design you've chosen for your renderer, ray-traced quality without a separate denoising step to manage, and accelerated content creation since you won't have to work around light leaks or wait for lighting to be baked into textures. No UV parameterizations or probe blockers are necessary either. Overall, these benefits should decrease iteration time and increase the quality of the final image. In addition to the features and benefits that the DDGI algorithm brings to the table, we've made a number of enhancements to the algorithm and its implementation in the SDK. I've listed them here and we'll go through each one next. First on our list is flexible resource management. Since game engines handle resources in a variety of ways to tackle their specific challenges, we made sure the SDK provides choices when it comes to resources. There are two resource management modes. In SDK Manage mode, the SDK internally allocates, tracks, and deallocates all the GPU resources it needs. This keeps the resources hidden from the application, but this black box design is easier to use for applications that don't require tight control over the resources. In Application Manage mode, the application is responsible for all resource allocation, tracking, and deallocation. Resource pointers are passed into the SDK, providing more flexibility for advanced applications at the cost of more responsibility. Next, to provide the widest possible support for arbitrary material and lighting models, the SDK doesn't require specific resource bindings or material properties. In fact, the probe ray tracing step is owned and implemented by the application, not the SDK. To make the ray tracing process easier, the SDK provides a number of utility and helper functions. One of these functions is DDGI get probe ray directions, which computes unique, low discrepancy, spherically distributed directions on the unit sphere. The probe ray tracing step writes its results to the SDK's radiance texture, which is then used in the probe update step. To improve light to dark convergence times, we've stored irradiance with exponential weighting. This moves irradiance into a nonlinear space that more closely matches human perception and also makes it possible to use a smaller texture format when storing irradiance. We expose hysteresis settings to give you control over the influence of newly traced rays when updating probes, ultimately giving you control over how quickly the indirect lighting will converge to the correct result. We've also included probe change and brightness thresholds. These thresholds are used to temporarily adjust the hysteresis when large lighting or brightness changes occur in a short period of time. When using these thresholds, you have tighter control over the lighting convergence speed, quality, and performance trade-offs. We've spent time tuning the performance of our implementation to achieve the scalability goal I discussed earlier. Here's an illustration of a GPU timeline for a hypothetical frame. I've added the new DDGI passes, probe ray trace, probe update, and lighting, and highlighted them in green. I've broken out the DDGI lighting pass in the illustration to show that this is a step that happens, but in practice it can be combined with an existing lighting pass. Keep in mind this timeline is hypothetical and isn't intended to represent performance. That's up next. Here's performance data for each of the 3 DDGI steps for 3 different GPUs. In the table, I've included performance numbers for the RTX 2080 Ti and RTX 2060 to show the two ends of the RTX GPU spectrum. Performance of all the other RTX boards will fall somewhere in between these two. I've also included numbers for the GTX 1080 Ti, the fastest last generation Pascal GPU, as a comparison point. Pascal GPUs do not have RTX acceleration. The test setup uses a scene I'm calling 2 rooms. This scene is distributed with the SDK, so you can run it and capture performance numbers for yourself to compare. I've placed over 16,000 probes in the 2-room scene and used the SDK's default settings of 144 rays per probe, 6x6 irradiance texture resolution, and 14x14 distance texture resolution. The lighting step is run at 1080p resolution. In practice, you'll most likely use way fewer probes than this due to a variety of optimization techniques like dynamically disabling probes. Keep in mind that this also means the total per frame cost in milliseconds in practice will likely be much lower than what is shown in the stress test. All that said, this configuration works nicely as a general scalability test. Okay, let's dig into the numbers. The probe ray tracing step varies from 1 millisecond on the 2080 Ti to a whopping 8.5 milliseconds on the 1080 Ti. The benefit of RTX acceleration is in clear view here, with the RTX 2060 more than 3 times faster than the 1080 Ti, and the 2080 Ti 8 times faster than the 1080 Ti. The probe update step ranges from 1.2 milliseconds to 2.8 milliseconds. Remember, this is for over 16,000 probes. That means the update time for a single probe is about 172 nanoseconds on the RTX 2060. If we zoom in on the probe update step, the SDK's compute shader code is about 2.5 to 3 times faster across these GPUs compared to the original implementation. This is accomplished by cooperatively performing computation and texture loads in thread groups and storing the results in GPU shared memory for fast access later. Zooming back out, the final lighting step is a full-screen raster pass that scales linearly with screen resolution, just like traditional irradiance probes. Pulling all of this together, we get the combined GPU time for the DDGI algorithm in our stress test configuration. These total times give us a way to understand how the algorithm scales across GPU hardware, as well as a broad sense of what kind of performance to expect. We see a 2x improvement going from the GTX 1080 Ti to the RTX 2060, and another 2x performance improvement going from the RTX 2060 to the RTX 2080 Ti. That's some straightforward scaling. Do remember that these numbers are for a stress test, and real-world scenarios won't need this kind of brute force configuration. This means the times you'll experience will be lower than the times shown here. Also, the DDGI algorithm is able to trade image quality for lag in the lighting update. If you have a fixed frame budget and your target hardware is having a hard time fitting in the budget at a specific quality setting, costs can be amortized over frames, ensuring you always hit your performance target. Now that we've looked at performance in a stress test scenario, you're probably thinking about optimizations for more common scenarios. We're including 2 optimization features in this release of the SDK along these lines. These features are early access, so expect them to be updated and improved in future releases. The first feature is called probe relocation. Any regular probe grid has a hard time correctly handling all scenarios, including the regular grid employed by DDGI. Probe relocation improves on this by maintaining a world space offset for every probe and using the results of the ray tracing step to attempt to move probes to a more effective location. The ray tracing results give us an idea of the surrounding geometry. For example, if a probe is surrounded by back-facing geometry, it's probably inside another object. In this case, the probe will more effectively contribute to lighting if it's moved outside of the containing object. The sample application includes an example of a simple linear descent optimizer that relocates probes positioned inside of geometry outside of the containing geometry. This happens over the course of several iterations. The second feature is probe classification. With a regular or semi-regular grid of probes, not all probes in a scene are going to contribute to the final lit result. Common examples are probes that are stuck in geometry, like walls, or probes that end up too far outside the interesting parts of a scene to be useful. A clear optimization opportunity is to not spend time ray tracing or updating textures for these probes. The probe classification feature maintains a per probe state value that marks the probe as either active or inactive. Inactive probes don't need to ray trace and update textures at the same frequency as active probes, and they may not need to do anything. In many scenarios, like open worlds or large sparse spaces, anywhere from 30 to 80% of the probes can be marked as inactive. Like probe relocation, this feature is in early access, so do expect it to evolve and improve in future releases. And there you have it, an introduction to RTX Global Illumination. Hopefully I've piqued your interest in Rtxgi, and I can't wait to see what you do with it. The SDK is available now. Go download it today. You can request access to the SDK by visiting the link on screen. You'll need to fill out a short survey to request access, and then once you receive an approval email, you can clone the full source distribution from GitHub. Get started by diving into the full source sample application we've included, and let us know what you think. Finally, I'd like to thank the talented team of people that came together to make the Rtxgi SDK a reality. And of course, if you have questions, feel free to send me a note on Twitter or post in the SDK's GitHub issues area.